Sorry about that, right, technical glitch with the camera there. Right, so that rocket science in question was a guy called Jeff Scott, who posts regularly on aerospaceweb.org and answers some questions that people ask him. And I found a really good web page that he'd put all this sort of stuff together. So basically my video is a lot about what I learned from that website, and I'm just trying to put it into the context of Unit 48 for those studying BTEC, okay? Because in my view, asking somebody to sort of, go find out how to calculate the theoretical coefficient of drag without any help is quite, especially straight from school, it's quite a tall order. So, what you end up with, you end up with coefficient of drag, your coefficient of parasitic drag, plus in this part here, right, this bit here, is your coefficient of induced drag. Okay, so this is the swirly bit at the side of the wings caused by the vortexes. Okay, and this coefficient of parasitic drag, this is basically your drag that is sometimes called pressure drag, right, which is just the force of the air pushing on the airfoil when you try to push that air out of the way, right, that's the force that's going to push back, okay, and the coefficient of that becomes the coefficient of parasitic drag. Parasitic drag, the definition being parasitic, that it's parasitic because it doesn't give you any lift, okay. There's various misconceptions out there. Some people, many years ago, I was taught that parasitic drag was all the little things sticking out on the airplane like parasites, like aerials and things like that, which technically it is, but that's not the proper definition of parasitic drag. Parasitic drag is the lift caused, it's the form drag plus the skin friction plus the thing called the interference drag. And interference drag is where you have different parts of the airfoil, so different parts of the airplane. So where the wing joins onto the fuselage, you'll get two airflows competing with each other, trying to occupy the same space, and that causes a slight increase in pressure and the energy of that air pushing it against each other, that energy becomes drag. Okay. When you try and push air, from a physics point of view, when you try and push air out of the way, yeah, you need energy to do that. You need to redirect air. So that airflow is coming at you, or you're hitting, well, technically, the air's staying still. You're coming along with an aeroplane and you're trying to push that air out of the way. When that air is pushed out of the way, it's going to create heat, it's going to create energy, and that energy is called drag. Right. So, you've got that drag there. Let's oversimplify this massively, right? Loads and loads of experiments, all aerofoils, yeah, curved airfoil like that, curved airfoil like that, another airfoil I can do, yeah. Well, there's two for you, okay, and then maybe let's do a supercritical airfoil. Oh, yeah, I'll probably get this wrong. Right, supercritical airfoil like that. Now, when it comes to this parasitic drag, if you look at them, right, if you look at the front profile of them, yeah, they're all pretty much the same, okay. How they redirect the air, how that slightly blunted nose of that airfoil, how that redirects the air. If you drew a very high speed, like the F-104 Starfighter we talked about before, that had like a diamond shaped airfoil like that, right? That would have a completely different value for this. But for these sort of standard size airfoils in subsonic flow, right, we work out that that parasitic drag coefficient doesn't really change a lot, and we end up with a figure that looks something like this, which is 0.025. Yeah. It might have a posh name that I haven't found yet, right? But what I found is that's basically from experimental data. If you're looking for a coefficient of parasitic drag for a standard airfoil, or a relatively standard airfoil at subsonic conditions, you come up with 0.025 for most conditions. So it's okay when you're looking for a theoretical method of working out your coefficient of drag to stick that number in. Another number that we're going to stick in is this E here, and this is Oswalds efficiency factor. Now, for high wing airfoils, for high wing aircraft, things like transport aircraft like C-130 Hercules and stuff like that, right, you end up with an Oswalds efficiency factor of about 0.8. And for low wing aircraft, so you're looking at like business jets and things like that, it can drop as low as 0.6. Okay, but if you don't know, because you're just doing an aerofoil, and this is a lot of this has to do with the kind of Here you will get a lot of interference drag, here you will get not so much interference drag. There's lots of other things that go into that factors, but basically if you're looking for a factor to stick in, right, you can stick in halfway between there and there. There's a nice average one which is 0.7. Right? Yeah. So for Oswald's efficiency factor, if we put 0.7 in there, we've worked out how to work our aspect ratio already. So our aspect ratio for that airfoil did was 4 before, so 3.14 times 0.7 times 0.4, sorry, times 4. The key thing on this bit here is this bit here. Because that coefficient of lift is squared, yeah, if that coefficient of lift that you use there is inaccurate, you're going to throw all of your other stuff out of whack. Okay? Right? If you use Prandtl's lift line theory, we know that this coefficient of lift will be slightly low because this is on top of the equation. We're dividing it by something else. If this number becomes lower, then when we end up with a coefficient of drag, or total coefficient of drag, will be slightly lower as well. Yeah, so that's basically when you stick all the numbers in. Again, if you notice, I've tried to go away from sticking numbers in here, right? Once you stick your numbers in there, you'll work out that your coefficient of drag, if you use Prandtl's lift and line theory to work out your theoretical coefficient of lift, using Prandtl's lift and line theory and thin airfoil theory, you will end up with a slightly lower coefficient of drag than what you would have with your experiments. Okay. Now for level 3, as long as you understand that, that's fine. We're not after a formula. Working out this constant here, okay, you could do, if you've got time, for my mind, for the assignment and things like that, working out that constant in between your two lines, you can do that if you want to, but that's, again, if you understand this and you understand why your data doesn't quite match up, then that's enough, right? That's what BTEC and that's what I would expect as a teacher to say. If you understand that, you're doing well. Okay, right. So let's recap. Yeah, let's recap everything. Let's just look at the graph. When you're calculating your theoretical coefficient of lift, there's not an equation that fits it perfectly. The closest one that you're going to fit to your curve, right, is your Prandtl's lift line theory, which is this one here. Okay, this one here. So if we'll do lift in blue. There we go. So that one there, right, is for your lift. And then we'll do drag in green. That one there is for your drag. Okay. And the main thing you're going to have to explain isn't so much this one. This one, remember these are in radians. Okay, right. But the main thing you have to explain, right, is what aspect ratio is and how you calculate it. And as well as that, this 0.025 and this 0.7, right? Remember 0.7, just to write on there, was Oswalds efficiency factor. And this, right, is based on lots of them, right, for based on experiments of standard airfoils in subsonic flow at moderate angles of attack. Yeah, so you might want to write that in there as well. Stick those numbers in, stick that into the formula, work out your coefficients of drags, and then you should end up with a graph at the end of it, and then the comparison of the two lines on the graph for your lift line and for your drag line should give you a comparison. The other thing you can do is you can do a lift to drag, you can do a coefficient of lift and a coefficient of drag polar, which will end up with a, if you plot coefficient of lift against the coefficient of drag, you end up with a curve basically that goes like that. Okay, and that's called a polar, and that's quite often used to compare different different aerofoils efficiencies at different angles of attack and things like that. So you can put that in, but I would stay away from the polars for now, because it's not going to show you the difference between these two theories. Okay, so if you go into if you start putting a polar in there, that will compare lift and drag about how efficient two aerofoils are. So that's worth doing if you've got two aerofoil shapes and you want to see which one's more efficient. Yeah. So for example, that will, when you put the two different curves on there, if you had an aerofoil like that with a flat bottom and then had a curved aerofoil, the difference in data that you should notice is that this one will produce more lift but will also produce more drag. Yeah. And the faster you go, yeah, this one produces more lift and then it stops producing more lift and just starts producing too much drag, and then this one, if you go faster, will produce lift and drag a bit more, kind of, not what's the word, in proportion. Right, anyway, a lot of maths on there, a lot to think about. Hopefully that's given you a couple of different formulas to use. That's introduced pointers a bit, and I'm trying to keep this down to level 3 standard. So please, if you're watching this on YouTube and you're sitting there going, oh, it's much more complicated than that. Yes, I know it's much more complicated than that, but we're trying to keep some things out so that learners who are coming straight from school can access part of this and go, right, and it doesn't kind of frighten them off and say, I'm not with you on that one. So if you notice there's no differentiation or integration of any equations on there, there's just basically, that's what it is, that's where it comes from, and sticking a couple of numbers in and explaining where those numbers come from. Okay, the Oswalds efficiency factor will go up and down depending on the shape of the airfoil, slightly, but it will be between about 0.8 and 0.6. So if you stick 0.7 in, given how small an impact it has compared to the coefficient of lift, the biggest impact on the accuracy of this one is going to be how accurate your coefficient of lift is. Okay, so that's something else you maybe comment about in your assignment. Right. My advice is, if you are not a student at Newcastle Aviation Academy and you've watched this video and you want to stick all this into your assignment, what I would do beforehand is check with your lecturer at your particular educational establishment, because it might be that they have another way of doing this. This is my way of doing it. Theirs may be different. They might want to look at different things, and you don't want to kind of overstep your mark when it comes to your research. Okay, so don't say, oh, this bloke in Newcastle Aviation Academy said I should do it this way, because that's fine. There are many ways to skin this particular cat, right? And that's one way of kind of looking at it. Like I say, thanks for watching the video. Hopefully that's given you some insight into the two theories, what they both mean, and kind of an easier way of, and basically if you pick up these books here, yeah, that if you can access this book and read these books, that's great. If you can't and you need it explained in a slightly sort of watered down format, hopefully this video has helped you a little bit. Thanks very much for watching. I'm going to do something which goes against my grain and actually shut up now. And I'll hopefully see you on the next video. Thanks very much. Bye.